Now we're going to run through some examples of actually finding an inverse, given information numerically, graphically, and algebraically. So let me start with a t-table. Let's say you were given a set of numbers or a set of ordered pairs, like 1, 2, 3, 4, 5, and maybe they have outcomes of -8, -6, -4, -2, and 0. So if you're asked to find the inverse, then as we discussed in our last example, I would swap my x's and y's. So this first inverse then would be -8, 1. That would be the ordered pair that would be the inverse of this ordered pair. The second one would be -6, 2. The third one would be -4, 3. The fourth one would be -2, 4. And our last one would be 0, 5. So we hope there's about 10 of those on the test. So numerically it's not a problem. And we have to come back and discuss whether functions even have an inverse. In fact, maybe I'll do that right now. So as we're looking at this, to be a function, you remember you couldn't repeat your x values. Well, to find the inverse, you have to swap x and y. So not all functions are going to have an inverse. In fact, it's okay to be a function if you repeat your y values, but what happens when you repeat your y values and you swap them and they become x values? Then they become repeated x values, which means that the inverse isn't a function any longer. So for a function to have an inverse, the function must be what we're going to call 1, 2, 1. So to be a function, you can't repeat your x's, and to be 1 to 1, you can't repeat your y's. So in other words, being 1 to 1 means for every one x, there's only one y, and vice versa. So our functions must be 1 to 1. All right, well, let's take both of these pieces of information and let's look at them graphically. So let's say you're given a graph, and it's going to be very abstract so that you can't use numbers. So if this is your function f of x and you're asked to find the inverse, then from the last example we see that the inverse is a reflection over this mirror. So I would have to draw the mirror myself because I can't do this very well. So then I would try to measure it out and do the best I can at finding a reflection of it. And then that would be its inverse. And I'll come back to this concept again later. But to be 1 to 1, graphically, what does that mean? Well, first of all, to be a function, it has to pass the vertical line test. But you can draw a horizontal line, and that would mean you're repeating your y values, and that's okay to be a function. But remember, when you swap, your y's become x's and your x's become y's. So if you're repeating your y's graphically and then you swap, that would force you to be repeating your x's. Or in other words, graphically, if it doesn't pass the horizontal line test, then it won't pass the vertical line test when you flip it. So then it would not be 1 to 1. Okay, but again, for now we're mostly looking at, if I give a graph to you, can you reflect it to find its inverse? All right, and then the last one we're going to look at is we're going to look at algebraically. How do you find an inverse? So let me start with a function that has several operations in it. So we have a multiplied 2. We have an x that's being cubed, and then we have a subtracted 5. So there's 3 operations in this. And for me to find the inverse algebraically, that means that I'm going to have a divided 2, a cube root, and an added 5. But not particularly in that order. So there is an exact order that it needs to be. So the easiest way to undo this function is to use the pattern that I'm pretty much using all along, and that is to swap x and y. So if we look at this first step here, this f of x is really y, so I'm just going to rewrite it that way. Now to find an inverse, then what I need to do is swap my x and y. So I'll come down here and this will become x, this will become y. And this really is the inverse. But we don't use it this way. What we want to do is resolve it for y. Because when we solve it for y, we physically have to undo all these operations to get y by itself, which forces us to undo them in the correct order. So if we look at this, to get y all by itself, I need to add the 5 first. So I'll add it to this side. So x plus 5 then is 2y cubed. And next, I would need to divide both sides by 2. So I end up with x plus 5 over 2 is y cubed. And then the last step, to get rid of the cubed, I am cube rooting. So I end up with y by itself is the cube root of x plus 5 over 2, which I'm going to rewrite as the inverse of f is the cube root of x plus 5 over 2. Now I realize that our inverse function is not simplified, but I want to leave it this way because I want to compare it back to the original function. So if you're looking at the original function, it's got a multiplied 2 and our inverse has a divided 2. Our original function has a cube in it and our inverse now has a cube root. And then our original function has a subtracted 5 and our new function has an added 5. And if I were going to check these then, I would have to plug one into the other and they would have to cancel out every single operation so that just x would come out.